Okay, guys. So, do you have any questions about the stuff we covered so far? All right. So, no.
You said you can just look at maps and there's practice problems, right?
Uh huh. Well, that requires me to think of an equation. I'm not prepared for that. So,
Why did you ask if it was
just testing.
okay? Oh, okay. Just making conversation.
Yeah.
He was being polite. We don't really want to know.
I'll help you at the end of class. Any other questions that don't involve massive amounts of thinking, since I've had teaching all day since 9 in the morning. All right. So, we left off talking about hydrogen bonds. You remember how many hydrogen bonds water can form?
4.
4, right? And yeah. So, remember what cohesion is? What is it?
They stick together.
Water's attracted to itself.
And why is water attracted to itself? And what kind of bonds are those? They're hydrogen bonds. Hydrogen bonds. No. So, and then there's the other property called adhesion. What is that? Water's attracted to other things besides itself. So, so you guys should know that. I'm going to probably ask you something like that on the test. Like, there are instruments that are designed around the properties that water has. Like when we use pipetters, when we measure the meniscus, things like that. So all of those are designed around these adhesive properties of water. Yeah. All right. So we're going to talk a little bit now about what temperature and heat are. So temperature is actually defined as the average kinetic energy in a system. So, if I had a glass of water, I'm measuring the average kinetic energy of the water molecules in that glass. So why does water have kinetic energy, and what does that mean? What does kinetic energy mean? Yeah, it means the molecules are moving, right? And the more energy they have, the faster they move, right? And the less energy they have, slower they move. Good. So, right. So kinetic energy is the average kinetic energy in a system is what we call temperature, and it's not the other way around. So if you guys, you have thermometers. So what happens when it gets warm outside? What happens to your thermometer? It goes up, right? So why does it go up? Why is it expanding? Because they're moving faster, right? They're spreading further apart. Even if you have like an old dial one, it's still just a piece of metal that's coiled up, right? And so what happens when metal gets hot? It expands and causes the dial to turn, right? And when it cools off, it shrinks, and so it goes the other way. So temperature is the average kinetic energy in a system. You could have a lake, right, and a glass of water, and they could be the same temperature. Let's just say it's 80 degrees, right? That means that all the molecules in the lake have the same average speed, kinetic energy. All the molecules in the glass of water have the same average speed, kinetic energy. Make sense? All right. Heat is different. So heat isn't temperature. Heat is a measure of the total kinetic energy in a system. And so let's say that you went to the gym and you were, benching 200 pounds and you did, 1 rep, 5 sets. So how much total weight have you lifted? 5 times 200 is 1,000, right? That's the total. What's the average weight that you lifted? 200. So there's a big difference between the total and the average. If you added up all the speeds of all the molecules in the lake versus all the speeds of all the molecules in the glass of water, which one has more heat? The lake, right? And so that means that it's harder to change that average temperature. So in other words, how much energy would you have to put in to heat up your glass of water? You know, you could put it on a stove or whatever. Yeah, 30 seconds. Can you put Lake Saguaro in the microwave for 30 seconds and heat it up, you know, to boiling? So water resists changes in temperature, right? Why is that?
Because it cools from the top down, and it doesn't have to do with that.
Not really. Yeah, okay, what properties?
But water remains the same whether it's hot.
Yeah, but it's so, you know, like most people have pools, and when you get in the pool, it's not the same temperature as the air, right? Because it resists. Right. So what? So why? I'm asking. So yeah, but what? So what? So why is water resistant to changes in temperature?
Because lazy doesn't want to move.
It's not lazy, but you're onto something. It doesn't want to move faster. Why?
Because they're so close together. Because they bond.
Okay,
They
let's
don't wanna
pretend
lose those bonds.
that you guys are water molecules, right? And if everybody grabbed each other, would it be hard for everyone to run away? So why would that? Why would you be grabbing each other if you're water molecules?
Because we're bonded.
What kind of bonds?
We're the hydrogen bonds.
Right. So hydrogen bond, because of hydrogen bonds, water resists changes in temperature because it's hard for molecules to move faster when they're being held by other molecules, just like it would be for you. Does that make sense? All right. So everybody understand the difference between temperature and heat? All right. So we can measure the changes that are the amount of energy that's required to change the temperature of the substance, and that's called specific heat. So water has a high specific heat, right? It's hard to change the temperature of water. Everybody knows why. If I ask you on the test, why is it hard to change the temperature of water? Hydrogen bonds, right? There's no other substance that's like this. You know, alcohols, ammonia, stuff like that. None of those have the hydrogen bonds, so none of those are resistant. Why are we mostly water? Why is it important that we're mostly water? So that's exactly right. So because water resists changes in temperatures, it helps us maintain homeostasis. What does that mean, that fancy word? Right. It maintains a constant internal environment. So our temperature doesn't fluctuate that much. And that's good because if it did, our proteins would change shape and we wouldn't be able to carry oxygen or do all kinds of things. So that would be bad. So you guys probably know what a calorie is. You've probably seen it on your nutritional label. You know, let's say a Snickers bar has 240 calories. What does that really mean? So a calorie is the amount of energy that's required to change the temperature of water, 1 gram of water, 1 degree Celsius. That's what the calorie is defined by. So how do they measure calories in the Snickers bar? Yeah, they burn it up. There's a machine called a calorimeter, and it burns up the Snickers bar and measures how much temperature has changed in, you know, a kilogram or a liter of water. And at some point the nutritional label changed, so it's not what you read are not really calories; they're kilocalories. So if a Snickers bar says it has 240 calories, it really has 240 kilocalories. So what does that mean? How many calories does it have? 240,000 calories. That means that the energy in a Snickers bar could raise 1 gram of water 240,000 degrees Celsius. Or it could raise 240,000 grams of water 1 degree Celsius. Does that make sense? Okay. It's a lot of water. How much water is 1 gram?
Not very much.
I mean, an exact amount.
It's one
Like,
Milliliter.
big.
Right, because that is also equal to one. Yeah, exactly. Remember, cubic centimeter. All the metric system was all developed based on that water. 1 milliliter of water weighs 1 gram. So that would be 240,000 milliliters, which would be 240 liters. Right, so a Snickers bar could increase the temperature of 240 liters of water 1 degree Celsius.
You just put it in
Well, you have to burn it up. Because what kind of
there.
energy?
So like when you put
So what
salt
kind-
in water, you help it boil faster. So what's the calories of salt?
Well, it doesn't have any, right? Because chemical bonds are what kind of energy? Kinetic or potential?
Potential.
Potential, right? So you have to break the bonds to release the energy.
So does the salt do to the water when you put it in there?
So it has to do with the way that the salt molecules interact with the water molecules and change their property. Because shape has a lot to do with property. We'll talk about that when we get to chapter 4. I had a similar question about someone in my other class said, why if you put salt on your arm and then rub ice on it that it makes it changes the pH and makes it acidic? I'm like, it doesn't. It just changes the temperature. That's why they put salt on roads, snow. So yeah, we'll talk about why that is. It has to do with the way that it changes the shape of the water molecule. All right. Everybody understands specific heat, calorie, and kilocalorie? Oops. Okay. So we live in Arizona. You guys are probably used to this. In the middle of the summer, you go to a bar or restaurant. What's going on the patio? Well, yeah, everyone's drinking probably, but they're also misters, right? So what are those magical things that they call misters, and why do they work here and they don't have them in, like, say, North Carolina generally, or Houston?
Because there's no humidity.
Right. So if there was what's humidity?
It's the amount of water in the air.
Gas.
Right. It's the percentage of water that's in the air, right? So at saturated, it's 100% humidity. That means that there's no more room for water to go into the air, right? So it would be worthless at high humidity because there's not a lot of water molecules that can turn into a gas. But here we have a relatively low humidity, right? And so when water comes out of the misters, it cools off the patio. Well, how does that work? No, not really. So it does vaporize. So what does that mean? So water's coming out of the misters. That's why they have misters and not just hoses coming out of there, right?
When it evaporizes, it takes the heat with it and rises up, right?
So, okay, so kind of, what's going on at a molecular level? Why does the temperature go down? What is temperature?
Temperature means measures kinetic energy.
What kind of kinetic energy? Total average what? Average kinetic energy, right? That means that different molecules move at different speeds that are coming out of that mister. So which ones are going to go into vapor? The ones that move faster or the ones that move slower? Okay, so if all the fast people on your football team left, what would happen to the average speed of your football team? It would go down, right? So if all of the water molecules that are fast leave, what happens to the temperature that's left behind? It goes down. So that's how evaporative cooling works. You're changing the average speed of the water molecules because the fast ones all leave into the air. Do we get it? It's the same reason that you cool down when you sweat, right? And this property is not just unique to water. Water resists going into gas, right? So if you put water on one arm and ethanol on the other, there's no hydrogen bonds in ethanol, so it just jumps off into the air, right? Which one feels cooler? Yeah, the ethanol. So that's how evaporative cooling works. All right, heat of vaporization, that is the amount of energy required to turn water, 1 gram of liquid into a gas, right? Water has a high heat of vaporization. Why is that? Why is it hard to make water into a gas? Hydrogen bonds, right? Because if you're holding on to somebody, it's hard for them to jump off into outer space, which would be kind of like what water molecules do. 580 calories. I don't care that you guys know that, but that's a pretty high number. That's why steam has so much energy in it, right? Because you can't create or destroy energy. You can only change form. So if you're putting tons of energy in to make water go to steam, that steam retains that energy. So it would be better to stick your hand in a pot of boiling water than to burn it with the steam. And that's why we have like steam engines and things that run on steam, because it's got a lot of energy in it. All right. You guys, we talked about water becomes less dense. Why is that whenever it's frozen? Right? But it's spreading out, right? Because it's making the maximum number of hydrogen bonds. What's the temperature that water's densest? No. So water, I mean, you guys know, you probably swam, down in a pond or a lake or whatever, and when you get deeper, it gets cooler, right? But water's really weird because it will get more dense as it cools off, but once it hits 4 degrees, it starts getting less dense. So that means that the temperature at the bottom of the ocean is what? 4 degrees Celsius. Europa is minus 273 degrees on the surface. What if we drill through the ice and we go to the bottom of the ocean there? What's the temperature? 4 degrees Celsius. Can stuff live with that in that temperature? Yeah, I mean, they pull up crabs on the deadliest catch all the time. What do the crabs live at? What temperature? 4 degrees, right? Because they live at the bottom of the ocean. All right. So I will probably ask you that on the test. What temperature is water densest at? All right, and that's important. We talked about insulation in here. All right, about snow. So if you're in a blizzard, and there's no trees around, best thing to do is sort of tunnel. It's a survival technique because, and that's why they build igloos, because ice is a good insulator. And so, it's a good thing that lakes and stuff freeze on the top, because if they froze at the bottom, it would still be frozen. Scientists estimate there would be about a half an inch of water left on the oceans from the last ice age if it froze from the bottom up. So it's a good thing. We'd all be dead. Any questions about that so far?
What you were saying about the water evaporates, the fast
Uh-huh.
is that why when you pump a lot faster you evaporate? Because it keeps the fast ones in and it makes more.
Well, it has to do with pressure, changes in pressure. Because you can make, if you decrease pressure on something, then you can make it boil at a lower temperature. That's why water boils at different temperatures at different elevations. That has to do with pressure. So. Yeah, because it changes the chemical properties of it. So
If
it
we
would.
were wanting to boil pasta entire wait for the water, just put some salt in there or something.
Yeah, so you can. You're basically lowering the resistance of it to convert into a gas, which is what boiling is, right? It's turning it into a gas. So yes, that's true. Any other questions? Okay. So we're going to talk now about water. Water's cool. It has a lot of properties that are important for life, like maintaining homeostasis, freezing from the top up, and so on and so forth. But really, the reason that we need water to survive is because it's a good solvent, right? I mean, your cells are pretty big in relative size to like the molecules that are inside of them. So if water didn't dissolve your, like, say, sugar, for example, then how would it spread into your cells? If I put a bag of sugar in the corner and then, I tied everyone up over here in the corner, how would how would you get to the sugar to live? Could you? No. So what's a way that you could make it move to you? So fill the room full of water, right? And then it would dissolve and move through the room. So that's what happens in cells, right? In fact, there are cancer drugs that you can give to patients, but if it doesn't dissolve into your bloodstream, then it's absolutely useless because it can't diffuse through the cells. It can't get to where it needs to go. It's like pouring sand in water. Does that make sense? All right. So why is water a good solvent? Okay, it breaks things down. How does it do that? All right, I'm going to ask you again. Why? Why does it weaken the structure? No, because that would change the pH. No, that's fine. I want you guys to think about this stuff. If you knew everything, you wouldn't need this class. So, I don't expect you to know the answers, but I do want you to kind of think about it, right? Because these are questions that you know, but you probably never asked yourself. Why do I have to drink water? What is it so special about water that I drink that instead of, isopropyl alcohol or ammonia? So when we talk about things that are dissolved, we're talking about two different components that are involved in that. The solute is what we're dissolving, and the solvent is what's doing the dissolving. So let's say we put salt in water. Everybody agrees that goes into solution. It dissolves. So what's the solute then? What are we dissolving? What do we dissolve? The solid's what we're dissolving. Yeah. And what's the solvent? So together, this is a solution, and that's a special solution called the aqueous solution. What does aqua mean? So an aqueous solution is one where water is the solvent. So let's think about what's going on here. We have NaCl. What holds those together? So it's an ionic bond. What's the charge on sodium? What does it mean if it's positive? Is it a cation or anion? It's a cation. What if it's negative? Good. So water has the ability to get in here and disrupt this bond between sodium and chlorine. Kind of like if you had a magnet on your refrigerator and you stuck a piece of paper in there, what happens? It'll fall off, right? Okay, a thick piece of paper. Yeah, you ruined my example. So water gets in there and it moves these two molecules apart, and it actually surrounds it. So it's kind of like, how David Copperfield can make the Statue of Liberty disappear. You think he's really doing that? Why does he use this sheet, right? It's an illusion. So water's kind of the same way. It surrounds the sodium and the chlorine to separate them, and it makes what we call a hydration shell. Which makes it appear like it's gone, like it disappeared, right? And that's what's going into solution. Does that make sense?
So it's a polar attraction. Polar covalent.
Well, yeah. I mean, yeah, and that's good because in nature, water is only good at dissolving things that generally have a charge, right? And so, bonds that have a charge are what kind of bonds? So ionic and what else? What kind of so does nonpolar covalent have a charge? Nonpolar means they share equally. So water wouldn't be good at dissolving something that's nonpolar, but it would be good at dissolving something that has a charge, even a slight charge, which would be polar covalent. Good. So ionic polar covalent. It dissolves. All right. So water surrounds us in a specific way. So if we have sodium that has a positive charge and we have water molecules here, it will surround it like this. And why is that? Right, because the oxygen has a slight negative charge. So what about chlorine? Does it surround it the same way? So the hydrogens surround it. And why is that? Because they have a positive charge. Remember, these don't share equally. The electrons spend more time around oxygen. And that's why it's considered a polar bond. That's why I taught you guys, well, hopefully you learned the difference between polar and non-polar. Because you'd be lost if you didn't understand that. Which half of you probably are, but that's okay. You can still learn it, right? Study, you got the whole weekend to study. All right. And so this shows you. I might put this drawing on a test, right? And I might not have NA plus here. I might just leave that blank. So I might ask you, what is the charge in this molecule here? How do you know? So because it's surrounded on the oxygen side. What about this one? It's negative because the hydrogens are surrounding it on this side. I'll probably make it in color. I don't know, it depends on if the department approves me spending money to make it color or not. Alright, so this is important, right? Water is able to dissolve things that have a charge. So let's say this is a molecule we're going to learn. I'm not going to tell you the name of it, but I want you to predict if water can dissolve this or not. How many people think no? It cannot dissolve, water cannot dissolve this molecule. So 3. How many people think it can? 6, and the rest of you don't really have an opinion. You can't make up your mind. You're on the fence. Alright, so the answer is, before I give it to you, right, we have to determine what kind of bonds these are, right? So remember, if it's polar, it has a charge. If it's nonpolar, it doesn't. If it's polar, water can dissolve it. If it's nonpolar, water cannot. So carbon is, hydrogen is, so the correct answer is, so this is a fatty acid, right? This is what's found in triglycerides and fats that are stored in your fat cell. Does fat dissolve in water? No. All right. So here's another molecule. This is found in your DNA. That's right. So the question is, will water dissolve DNA?
Yes.
How many people think yes, water can dissolve DNA? Dissolve it, yeah. Dissolve it just like salt.
Like gone.
Well, it's not. Things aren't gone if they're dissolved, right? It's just a magic show.
Well, yeah, because it ruins the sample if you put it in water.
Okay, so how many people think DNA can't be dissolved with water? It's okay, you know. So the answer is anything that has a charge, water can dissolve. So DNA is water soluble. You put it in water and it will dissolve.
What is
The what?
the 10?
Where? No, that's an oxygen.
Oh,
That's my oxygen. Don't judge me.
That's a positive hydrogen.
All right.
That's drawing.
So that's why it's important you guys can predict whether things are, polar or non-polar, because you need to know if water can dissolve it or not. And it's not just for this class. It's if you design a new drug. Let's say you design a cancer drug, but it doesn't go into solution. How are you going to get it into the cells? How are you going to get it to move in people's blood? Is it like you're going to pour a bunch of sand in their blood? Is it going to move around very well? No. So you have to think about these things whenever you're, becoming, biochemist and things like that. Or if you're in the medical profession and you're trying to give people drugs through clinical trials. So we have terms for this. The terms are hydrophobic and hydrophilic. So what does phobia mean? You guys were just talking about arachnophobia, right? So what does that mean?
Doesn't like it.
Yeah, you're afraid of it, right? Like me, I'm afraid of spiders. I'm not afraid to admit it.
So I know what to get you.
I'm not afraid of cobras, like, rattlesnakes, no problem. I used to catch those things by their tail and, mess with them all the time. Spiders, I'll run away. I'll jump up on a chair. I don't know. Did you guys see, I was telling my other classes, but, did you see, I saw this on, I don't watch Ellen religiously because I'm not at home. My mother-in-law does, but I saw this on Yahoo. So Channing Tatum, he's afraid of porcelain dolls. That's his biggest fear. So I think he's more of a wuss than I am, right? Because he's afraid of.
So I've seen like worse than that, like on Oregon, they bring people that are scared of pickles.
Pickles?
Maybe little pickles and she stormed off the stage.
Oh my goodness. So anyway, that's a phobia, right? What's the phobia of porcelain dolls called? What's the Latin term for that? I'm not sure. And then philic, right? That means you're loving. So hydrophilic means that you're water loving. Hydrophobic means you're water fearing. So water likes itself, right? So that means that things that can be dissolved in water, like water, are hydrophobic or philic. Can dissolve in water, they're hydrophilic. If they can't dissolve in water, they're hydrophobic. So that's basically just another term for saying something's polar or nonpolar, right? All right. So when we're making up solutions, a lot of times when you guys do clinical trials, these solutions are measured in molar. So this capital M means molarity, right, which is a value of the amount of solute. So it's and this is in a term called moles, right? They're not like the things with whiskers and stuff. Yeah. Of solute per liter of solution. All right, so a mole is just basically taking the molecular weight in daltons and then just crossing off the daltons and putting grams. Right? So it's pretty straightforward. What does a mole of hydrogen weigh in grams? All I have to do is take the molecular weight in daltons and then just change it to grams. So what's the molecular weight of hydrogen? Well, we'll just round, right? So let's say it's 1. So the molecular weight of hydrogen is 1 dalton. So we cross that off, we say that's 1 gram, and that is what a mole of hydrogen weighs. Does that make sense? Let's try sodium chloride. So what does a mole of sodium chloride weigh? So we take them individually, sodium and the chlorine, so we have 23 plus, well, I'm just going to keep it at 35 and a half. So together that's 50. And then that's daltons, right? But I'm just going to change it to grams. So this is 1 mole of sodium chloride. So if I asked you to bring me a mole of sodium chloride, you'd weigh out on a scale 58.5 grams. What about a mole of water? If I asked you to bring me a mole of water,
H2O.
how many grams of water would you bring me? 16 plus 2 is 18. That's right. 18 grams of water is 1 mole of water.
So basically almost like the mass of
Yeah, it's the molecular weight, yeah, the mass number in grams. That's right. Okay, so let's say I wanted you to make a 1 molar solution. You know, this is relevant because you guys know that they're IV bags, so they give you straight water in an IV. Okay, yeah, and it's a specific amount, right? Usually it's measured as a percent or a molarity. So let's say that, and this is not real, but let's just say we're in, you know, I don't know why I like to say Ecuador instead of El Salvador, but let's just say they're both. So Ecuador, El Salvador, we're doing a mission, and there's a horrible bus accident. People are bleeding and they're losing all kinds of fluid, and you're down there with me, and I'm like, we got to make 1 mole solution of salt water so that we can give these people IVs so they don't die. So I'm like, let's do it. Go. So what do? Come on, people are dying. 2 or 3 already dead now. So I want 1 liter of 1 molar sodium chloride. So you're going to go out and you're going to weigh out 58.5 grams of sodium chloride, and then you're going to pour that in a liter of water, and you just killed everyone else. Why is that? Right, so it's not liter of solvent, it's liter of solution. So let's say that we had, here's our you know, whatever we have, our bucket, and it has a 1 liter mark on it, right? So well, it is in El Salvador. So if you poured 58.5 grams, which is about, you know, one of those containers of salt, you know, the big containers, you poured that in there, what would happen to the liter mark? It would be the same as you get into your bathtub with it filled all the way to the top. What would happen? Yeah, so adding all that salt in here makes this level go up. So you've given your patients the right amount? Less? More? Less, right? Because you got too much water in there. So this isn't an accurate value at all. What you have to do is, well, you have to fill it up to a smaller amount so that it will dissolve, and then you add water up to 1 liter. So now that's solution, right? Liter of the solution is the salt plus the water. That's how you make a molar solution. Does that make sense? So don't screw that up, right? You kill a whole bunch of people on accident, I'm sure, but you know, because you didn't pay attention in 181 class. Yeah. Which would cause their cells to swell and burst.
I don't get the equation. What happened? Mathematically, it makes sense.
What do you mean?
Like, so you put how much you put.
What isn't it
how much
math?
salt did you put in there?
Okay, so
Sodium chloride did go in there.
so we put, how much is that? How much is sodium chloride?
9.5.
What is it? What do we call that?
One mole.
Okay, so we have 1 mole divided by 1 liter. 1 divided by 1 is 1 molar. Mathematically, it doesn't make sense?
No, in the
Why do you take water out as well, so not you never put that water back in there?
Because if you fill it all the way up to a liter and you pour the salt in, it'll be too high. Does that make sense?
How's that gonna dissolve?
But still, but isn't that amount?
No, because
matter
you have
doesn't
too
disappear.
much water in there.
But matter's not going to disappear. The salt's not going to disappear, and all of a sudden you can fill it up with a liter of water. It would be in there.
The solution would
Come
be
on.
sweet.
So you know that if I put less water in here and dissolve it and then fill it up to here, that it's going to be more salty than if I filled it up to here with water and poured salt in.
Like,
And
okay,
now the
say-
new volume's up here. It's the same thing with
But like, you
with,
have a
like,
cup of
tea.
water, you have a cup of water and you put a cup of tea, so hot tea, with
Okay.
sugar in there.
Yeah.
The water level rises.
right?
When you dissolve it, it doesn't go back down.
Exactly.
Okay, so over here you're saying you're going to dissolve it in that water, and then when you add
Dissolve
the
it
water.
in less than a liter.
Dissolve it
Yeah,
in
it's
less than a
less than
liter.
but then he's going to add the same water. But then if it was
No,
a
he's
liter,
only gonna add water till it reaches the 1 liter mark.
It's gonna be less water.
Yeah.
Because you're gonna dissolve it in
see,
smaller
I'm thinking you're
amounts of
saying you're going to put the same amount of water and the same amount of salt.
No, no. Because if I put in the same amount of water, it would go above that.
So dissolve it, then add water to 1 liter.
Dissolve it and then add water to the 1 liter mark. Right, or no matter what you're making, right? This could be potassium chloride. It could be, you know, a drug. Drugs are measured in moles per deciliter of blood volume. So if you're doing a clinical trial on a drug and you want to measure half-life, that's how you're going to measure it. And if you don't know what a molar is, a concentration, you'd probably get fired because they're going to be like, you're no good for our clinical trial. So what if I didn't want 1 molar? What if I only wanted a quarter molar? And I didn't want 1 liter. I didn't want to waste it, right? We only had enough bodies that we just needed 500 milliliters, half a liter. So now I want a half a liter of 0.25 molar salt. What do I do?
So when you do 25% of 58.5 grams.
Okay, so if we do, so you're going to divide this by 4, right?
Yeah.
That's the same as 25%. So I don't feel like doing long-handed division.
I can add it for how many
14.625. Okay.
And then you put that in a solution. You just dissolve it in a little bit of, and then a little less than half a liter, and then you put the water up to half a liter.
Okay, so then we're going to put this at 0.5 liters. So this is a quarter mole in 0.5 liters. So if we divide that out, it should equal 0.25, right? grams. That's a quarter mole. So that's the amount here. So that's not right.
So you gotta divide that in half.
So what you want is you want a quarter liter. So how much salt do you need then? You need half a liter. Right. So then if you're 1 molar, if you're going to do a half a liter of 1 molar, then how much salt would you use? If you're going to make a big jar of sweet tea and you're put like 100 grams of sugar in there, if you only want to make half of a jar of sweet tea and make it the same as sweet, how much do you put in? Half of that, right? So that's 50 grams. So automatically we want half of this, which is my calculator says 29.25. Okay, so now I want how much of this? All of this would make it 1 molar, wouldn't it? No, this is a half a molar into a half a liter. So if we do half a moles and half a liter, 0.5 divided by 0.5 is what? 1. So we haven't changed anything. All we've done is reduce the amount of salt in half. We've also reduced the amount of water in half, which keeps everything equal, which is what we just talked about, right? If you had 100 grams of sugar and you put it in a liter of tea to make it sweet, if you wanted the exact same sweetness and half the amount of tea, how much would you add? So it's the exact same. Halving this doesn't do anything if you're halving the volume. It makes everything the same. So what do you have to do now if you want it to be a quarter of what that is? So you have a half a liter. No, can't change that because that's the amount I need to save all these people. You don't half it. What do you do? Right. So now you divide that by 4. So what is that? 7.31, which is how much of this? An eighth, right? We did a half and a fourth. So what's an eighth? 1 divided by 8 equals, and then this is divided by a half. What's the answer? So that's how you correctly would make 0.25 molars of. Everybody's dead. They're all dead. So how are you going to get faster at this? There you go. All right, so I'll have a test question similar to this. So make sure you guys know how to do it.
What is that called? I was going to say,
So this is all different.
This is I mean, you guys are going into medicine, right? This is what you signed up for.
Yeah.
Or even if you're going into biology. I can't tell you how many molar solutions I've made over the course of my life. Probably 500,000. So this is, you're going to do this all the time. And math is the hardest thing, I think, for everyone to do, is doing these solution calculations. But it's really important because if you don't do it right, what happens to your patients? They die or you mess them up really good. Remember? 225,000 people died last year from messing up. All right, so let's try one more. So I want a 1 molar, I'll make it easy on you, solution, aqueous solution, right? This is sucrose, table sugar. So tell me how you'd make it. I'd say 90% people aren't. Oh, that's cheap.
Oh, sorry.
That's why I flipped it back to the other slide.
Sorry.
Okay. All right. So,
I did the math. I didn't
all right. Let's.
Started to, and then you said people aren't getting it, so
I knew how to do the math, so.
All right. So let's do this. So the first thing we have to figure out is what does a mole, right? Because the definition of molar is moles of the solute, which is this, right, per liter of solution, which I told you it's aqueous. So what's the solvent? Water, right? So we're going to make up a liter of 1 molar solution of this. So what's a mole of sucrose weigh?
It's 342 grams.
Okay, so how'd you get that?
Carbon, and then 12.
Okay, so we have 12 carbons,
And a weight of 12 daltons.
and they weigh 12, but we convert that to grams. So 12 times 12 is 144 grams. So that's the carbon. And then the hydrogen part is we have 22, and they're each 1 gram. So that's 22 grams of hydrogen. And then the last one is oxygen. And we have 11 oxygens, 16 grams.
176.
So 342 grams is what 1 mole. So if I ask you to bring me a mole of table sugar, you'd have to weigh out 342 grams. I'm going to ask you some of each, because you need to know how to do all this stuff. Right? You can't get to the other one unless you know how to do this. It's fair. Yeah, I mean, I've been doing this for a long time, so I'm not going to change the way that I test generally, because I think it's important. I don't want you to go out and kill people.
So can we do another example of what we did before this?
No, we'll do. I'll come to my office hours, right? Next time.
Work in your office hours.
You do? All right. Well, we'll talk after class then. All right. So here's the correct answer. Again, remember, if you guys didn't have chemistry, you can get that book, Chemistry for Biology Students. It has practice problems in that, and you could probably look up online, practice problems for calculating molarity of solutions. I'm sure stuff will come up, but I'll be more than happy to stay late. And that goes for anyone else. All right, so this is a made-up thing, right? A mole is just a made-up thing. So someone said, okay, well, I'm going to just convert the daltons into grams, and that doesn't really tell you how many molecules are in a gram. Yeah, it's the same way they came with the metric system, right? They didn't know how long the meter was going to be. They just measured this distance and then divided it by 10 million, and whatever came out came out. And so this is the same thing. So there's this guy named Avogadro who apparently was incredibly bored and wanted to know how many molecules are actually in a mole of a substance. So he counted each one. Just kidding. But, he did some mathematical equations on it. And it turns out that there's 6.022 times 10 to the 23rd atoms in a mole of a substance. Not that you'd ever need to know that, but, I'm just letting you know. So that's chemistry.
So was it like a trillion?
So, it's bigger than that. Because a trillion is 12 zeros, right? Google is 100 zeros. So it's somewhere between a trillion and a Google.
I'm getting there.
All right. When you figure it out, you let me know. And I'll put it in my slide. All right. Molarity, everybody understand that and how to calculate it? All right, that's good. So we talked about this, 1 molar solution of sucrose, and you guys would know that you don't pour the sucrose into a liter of water, right? You have to dissolve it first and then bring it up to the liter mark. All right. So the next thing we're going to talk about that has to do with water is acids and bases. You guys probably know what an acid is and a base. You know that acids have the ability to cause chemical reactions to occur. If you watch Breaking Bad, what they use muriatic acid, they poured it on bodies, and what happened? Yeah, and then it dissolved the tub and the floor and everything else. So acids can have powerful reactions, and so can bases. So what makes an acid and a base what it is? And what makes it behave the way it is? And so we'll start off with that word pH, right? Because pH is an indicator of the acidity or the alkalinity, which means the basicness of a solution. So the word pH comes from process, which in French is power, hydrogen. So pH is a measure of the amount of hydrogens, and it's not hydrogen itself, it's H+. So it's the hydrogen ion. Remember that word, ion? So the more hydrogen ions we have, if the number of hydrogen ions go up, the pH goes down. I'll explain why in a second. If the amount of hydrogen ions goes down, the pH goes up. Right. So increasing hydrogens makes something acidic, decreasing hydrogens makes something basic, but it's actually the concentration of the H pluses in the solution that determine the pH, the acidity or the alkalinity, the baseness of the solution. So in order to understand this, we have to go back to our friend water.
So is water considered to have pH?
It does have a pH.
It's 7, right?
It is 7. That's correct. And there's a reason for that. So let's think back to chapter 2. You guys know that hydrogen and oxygen, they share electrons, but they don't share equally, right? And so the electrons spend a lot more time around oxygen than they do hydrogen. In fact, sometimes they spend so much time around oxygen that they forget to share with one of the hydrogens. And what happens if you don't share? Well, you can't kill an element. But what creates this bond? Sharing of electrons, right? So if you're not sharing, you no longer have a bond. So hydrogen is no longer bonded to the water molecule. And this happens at a pretty constant rate. The rate that this is formed it's measured in moles. So it's 1.0 times 10 to the minus 14 in a solution That's the amount of these molecules that dissociate. And that's measured, and it's a constant, and you can ask a chemist how they figured it out, and I really don't care. But just trust me that never varies. It always happens that way. It's just the nature of the beast. When this comes apart, this loses its electrons. So what is it now? What's its charge?
Positive.
It's positive, right? Because it was sharing with these guys, and they kept the electron. So now it only has no electrons. It's not sharing at all. These kept the electrons, so what is the charge on this now?
Negative.
Negative. So that's why I drew this as H plus and OH minus. Right? Now, together, the concentration of these is always 10 to the minus 14th. In any solution, it's the same. This never varies. This is the value. So these multiplied together are this. All we care about is what this H plus is. So what is that value? If we know that this is true, these two multiplied together are that.
What is which value?
What's either one of their values?
1, 2, 7, negative 14.
Half of
No.
that. 1.0 times 10 to the negative 7.
That's right. So this one, hydrogen, is 1.0 times 10 to the minus 7th, and the OH value is 1.0 times 10 to the minus 7. That's how we figured it out, right? Because we know that this is water. So we know that anytime this is formed, one of those is formed, how many of these is formed?
1.
One. Because this is only formed if this comes off. It's a 1-to-1 ratio. They always have to be equal in pure water, right? There's no way I could create extra hydrogens. So H plus equals OH minus. Together you multiply them, and that's the same as adding. So if you multiply exponents, you add them. If you don't know that, then you should probably brush up on your exponent math. And so the pH is actually it has to do with an inverse log or whatever, but it doesn't really matter. The easiest way to do that is just drop the minus. So the pH of pure water is 7 because the H plus value is 10 to the minus 7.
So you can figure that out with anything.
Sure. You'd measure the free hydrogen. So let's say that it isn't water. Let's say it's something else. And I measured the value of the H pluses at 10 to the minus 6th. What's the OHs then?
It's going to be 6.
6 plus 6 wouldn't make 14. It has to be negative 8, right? And then what's the pH?
6.
Because we're measuring hydrogen. So the rule is that if these are equal, it's a neutral solution, right? Water is the only true neutral solution because these are formed at exactly the same rates.
So with everything, it has to equal 1.0 times 10 to the negative 14. Everything.
An aqueous solution, yeah.
Only aqueous solution.
Okay. I don't want to get into like too much of a technicality, but I'll just say, yeah, that's true. All right, so if the hydrogens are higher, what's bigger? 10 to the minus 7th or 10 to the minus 6th? So how many people think 10 to the minus 7th is bigger? How many people think 10 to the minus 6th is bigger? Yeah, you're right. 10. Right? So if we did 10 to the minus 3rd, that would be right 1, 2, 3. And if we did 10 to the minus 2nd, that would be. And if we did 10 to the minus 1st, that would be. So 10 cents is bigger than 1 cent, right?
So the lower the pH balance, so if
It's not a balance.
Or the pH
That's too
level.
many commercials.
I'm sorry, the pH level.
Yes.
So that, the 10 to the minus 6 and 10 to the minus 8, that would be considered
This is acidic, yes, because
higher.
this is bigger than 7.
Okay.
Negative 7. Not that, I'm not saying 6 is bigger than 7, right? But 10 to the minus 6 is bigger than 10 to the minus 7.
-8.
Right, so that's why the pH scale is all screwy, because it's negative exponents. So that when the number goes down, it's actually, the amount is going up. Does that make sense? So that's why it's confusing. So if you want to make an acid, then what do you have to do?
You want to
Less water.
Yeah, you have to add hydrogens, right? So, and if you want to reduce acid, you got to take hydrogen out, right? So it's as simple as that. So if the pH is bigger than 7, it's a base, because that means the number's smaller, it has less hydrogens. If the pH is equal to 7, it's neutral. If the pH is less than 7, it's an acid. Does that make sense? All right. And that's the only thing that can change it, right? So can you drink water if you have acid indigestion? Is that going to help? That's not going to change the pH, because you're not adding hydrogens into your stomach. The only way that you can do that is to either add hydrogens or take them away.
What about milk?
So it depends on what's, I don't know the chemical reactions or properties of milk, but I would imagine that milk probably does not change the pH.
So basic.
A base? Yeah. That's actually a buffer. We'll talk about that in a second. Okay, so everybody understand the difference between an acid and a base? All right, so things that are acidic are things like muriatic acid, which is also known as hydrochloric acid. We use it for your pools. So hydrochloric acid is HCl. What is that made up of? H plus and chlorine minus. So I'm pouring that into a solution. What am I doing?
You're bringing down the pH.
I'm adding hydrogens, right? So I'm making it more acidic. That's how it works. That's why it's an acid. And remember we talked about your stomach? The way that your stomach makes the liquid inside of it more acidic is by putting H pluses out of your blood into your stomach. Oh, dang it. That one's flashing, so it won't turn on. So you guys will just have to look on that one for a second. The rumor is that we're going to get laser projectors. I'm not sure if that's going to be like laser lights, like if I could write stuff in lasers on the board or whatever, but we'll see. Alright, so sorry, still flashing, I can't turn it on. So I would direct your attention to the screen on the right, my right, your left, or your laptop. Maybe you guys might want to bring those, considering the issues we have. So a base would be something that pulls hydrogens out of a solution, right? So sodium hydroxide is a really strong base. And so sodium hydroxide is made up of sodium and, right, remember, and that's the same molecule that was formed when water dissociated. So when we pour this into water, remember, water also contains H pluses and OH minuses at equal numbers. So when I pour this in, what happens to these hydrogens? They're going to go and combine with that to make water. So what am I doing to the number of H pluses in the solution? I'm decreasing it, so that by definition is a base. It's taking out H pluses out of a solution. So you'd have a higher pH. It'd be more of a base. And ammonia does it directly. So ammonia can actually take an extra hydrogen on it. Remember, nitrogen's that weird molecule that has the extra holes that it shouldn't have. So what now? No, the water is always going to have the same pH. It'll always be 7.
So more, it's the hydrogen, not the water.
So if you had more water and you added less of this, it would affect that solution less, if that's what you mean. Yeah, so it wouldn't change the pH as much. But water itself doesn't change the pH. The only thing that changes pH is adding H pluses or taking them out. That's it. There's nothing else you can do. So this is kind of just telling you the pH scale. Your stomach acid is about 2. Soda, beer, stuff like that. Soda has carbonic acid in it. That's just formed by bubbling carbon dioxide and water. So that has a pH of about 3. Urine, about 6.2.
So is that why you drink magnesium citrate?
I thought you were going to say urine.
No. So when you drink magnesium
Bear
citrate,
Grylls.
is that why you get diarrhea? Because you put ice with acid and you get that reaction?
I don't think so.
But no, because when you're constipated, they tell you go drink some magnesium citrate or take like I don't know what they're called. Like
Right,
glass
yeah,
or
like,
whatnot.
yeah, milk of magnesia,
But the
put them in
magnesium
water.
itself, it acts with the acid in your stomach, and what makes you get the runs?
So that has to do with the reabsorption of water in your system. I'm not sure that those two are
What
related.
does it produce? What is magnesium producing with your stomach and the acid, the gastric acid?
Well, I'm not 100% sure. I mean, it probably could combine with a lot of stuff. It's not, it's going through your entire system. So I'm not an expert on. I'm sure that it can interact with a whole host of things. Magnesium isn't like limited to just one reaction. Like the body and your cells are complex systems. Magnesium is required to change the shape of the enzyme that copies your DNA, and it also is required to change the shape of the enzyme that breaks down DNA in the lysozyme. So the magnesium could do those, right? And like a whole host of other things. So you can't just like say it's just isolated to one thing, I don't think. Does that make sense? And it really doesn't have anything to do with pH, because it's not going to change. Well, it could change. It could buffer your system, because calcium can do that. And so they're in the same group. But I'm not 100% sure. I'll have to look it up and get back to you. Remind myself, correlation between milk of magnesia and pH and diarrhea. It's my study session for tonight. Well, yeah, you dilute out poison, but that doesn't really have anything to do with pH, right? That you're just diluting the amount, the ratio of whatever toxin it is to the level of water, and then you'd hope that they would urinate it out, because if you kept it in the system, it wouldn't change anything, right? Like if you sat around and drank water and didn't go to the bathroom, you would saturate your system with water, and you would die. You heard about that lady who was in the contest to win the Nintendo Wii? It was like, hold your Wii for a Wii, and she had to drink water, with other contestants, and she died. And then she died because, I drink water, a lot of water all day, but I don't die. Why? Because I go to the bathroom. So as long as you're flushing your system, you'll dilute out whatever toxin it is. All right, so I can tell from your rustling that I'm out of time. So we'll pick this up on Tuesday.